Okay, let's go. The plan as usual is to solve some problems without local testing. And if we solve all the problems of the contest, it's a win. Okay. So last time we solved this contest, it was interesting. The last problem was pretty interesting. And I solved this contest just when this contest was called on, so it's just I solved it online. But we still have enough contests for a few more streams. So let's go. You kidding me? What? That's the problem? So, okay. Did we miss something? Just calculate, okay? No hidden tricks. Okay. It's quite unusual to have that specific problem. So usually in contests, the problem is a little bit more complicated. So you need to understand what's going on. This problem, you just need to calculate the value given. So that's strange. Given an integer's computer. Okay, that was a strange contest. Okay, in this problem at least you have this trick. So if you need to check if if your product exceeds this value. So there are many. The easiest way to solve the problem is to use Python, I think. But I will not use Python. I'll use C++ instead. So that's how it's supposed to be. Yeah? But then you need to check if this result is more than 10 power 16. What's the problem? So I can do it like this. Is more than like this. But it's not working this way because if it exceeds this value, so here I will have integer overflow. Yeah. So if you just multiply two big integers, they will not fit in this type. So there are many ways to check this. Let's see. What is the easiest way? I think the easiest way is like this. So what I need to check? I need to check that res multiplied by x exceeds this value. Let's do it like this. Is at least one. Yeah. So how to check if res multiplied is this? I need to check the x is at least this divided by res, like this. So if this is satisfied, then this is satisfied. Okay. So instead of checking this in equation, so here I will have integer overflow. I will check this constraint. If this constraint is satisfied, then this is satisfied. That's the plan. No. I need to. This is rounded down. I need to round it up. Yeah. So it's plus or this minus 1 like this. So I can this this. So just set plus 1. Yeah. Is round up really necessary? Yes, it is, I think. Because if I round it down, basically, let's do it again. So I want to check that this is at least this divided by this. Yeah. So that's what I want to check. So I have this value. This value is integer, and I need to check that this integer is at least this floating point value, right? So this number is not integer, and this number is integer. So if we check that given integer is at least this floating point number, you need to round this floating point number up, yeah, to make a sale of this number. So if this is okay, sorry. So you take this, and this will be exactly like this. Okay. Oh, sorry. Use log formula. Yeah, that's another way. There are many ways to solve this problem. Another way to solve this problem. I'll try several. Okay, let's try several things. So let's first try this. Let's try different ways to solve this problem. This is one of the possible ways to solve this problem. You can calculate. These in. Oh, okay. Sorry. I have too many thoughts in my head at the same time. So let's first check. Let's first try this, and then I'll show you some another ways to solve this problem. Again, so I need to solve this problem. So this is exactly like this. Yes, plus raised minus 1 divided by this. Yeah. And here I just plus minus 1. Do it here, then plus res. You can get it out of this. So this will divide by res plus 1. It looks strange actually. No, it doesn't look strange. So if x is at most this, then I will have multipliable by res, and I will have value less than so this value plus 1. It will exceed this one. Yeah, yeah, makes sense. Yeah. Oh. Okay. So what's wrong? That's embarrassing actually. Only zeros? So what's the problem if it contains only zeros? Why it's special case? Res may be 0. If res is 0, that may be a problem. Yes, if res is 0, it may be a problem. Then I divide by 0. You can divide by 0. Okay, let's try this. But actually, No. Yeah, even if there's a 0, it will not cause the wrong answer. Yeah. Housing floor plus 1. It's not floor plus 1. Here I have 1, here I have 0. So it's slightly different. You forgot to use long. Should I use long here? I think it's supposed to be long because it doesn't fit in. Do I need to specify it is long if this constant doesn't fit in integer? It's not working on the last sample. It's not working for the last sample. Oh, that's so embarrassing, sorry. So, okay. So even if it exceeds this value and I have zeros, yeah. Okay, I tried to avoid this. We had this similar problem last time, yeah, I remember. Yeah, we had the same problem last time. So if you have 0, then if during, so when you multiply some prefix, you have a value less than this, it's not a problem, because after this you will get some 0 and the rest will become 0. So the product is not exceeds this standard because the product is 0. Yes. Another way is to use integers to pass. We will try both all these techniques. It wasn't the problem. Ah, my bad. That was. Oh. Okay, so that's one way to solve this problem. Yes, another way is to solve integers. Yeah, we do it like this. You can just use it everywhere. Yeah, that's another way to solve this problem. And finally, what you can do if you don't have this 128-bit integers, you can just use doubles instead. So you can use something like this. You can use long number, and you can use like this. So if this double value is not exactly the product, yeah. So let's check if my value is much more than, like for example like this. So if so in this value we have some accuracy problems. So you have some error, yeah. So, but if this double value exceeds twice the number you were looking for, this basically means you have the overflow problem, or you have something like this. Yeah. So. Yeah, I think that should work. Okay, so again, what we're doing here, we calculate this long value in this variable. This will be our answer. And in this variable, we calculate the double value. So this double value will be about the same as this race, but not exactly, because if you have the overflow problem, then this value will have overflow, so it will not be the product you're looking for. And this will have some error because it's not integer, it is floating point number. But if it exceeds this value, it can be because of the floating point problems. If it exceeds this value, it means you have you overflow your limit. So you check this, and if your value is is near the border you're looking for, then this value will be correct. So you check that this value exceeds there. So this is like the first check. This is like a rough check of if you exceed your limit, and this is like more precise check that you exceed your limit. It's another way to solve problems like this. Okay, so we lost the contest basically, but we will continue. Okay, it's fractional part. What? Compute output will be truncate fractional part and print result as integer. Okay, so I have one integer variable and another variable with 2 digits after the decimal point. It's very strange contest. It's more like educational contest, how to deal with different multiplication problems. Okay, let's do it. So we have two variables. So what I will do, the variable b is floating point number, but it always has two digits after the point. So I will multiply the second number by 100, and I will have two integer numbers instead. So let's make it longer. I can solve it. Can I do it like this? So I want to do it like this. I'm not sure about rounding problems. How to round in C++ to the nearest integer? Is there some round to nearest? Like this? I'm not sure about plus. I don't have C. Like I want to have round, just round. Okay. So I'll round to nearest integer. This will avoid all the problems near the integer, because when you have number like this, it is not stored in the double exactly, because in double number you always have this error. But when I multiply it by 100, it should be integer, but it will not be integer. It will be about the integer. So you have integer plus or minus epsilon. And to avoid all these plus minus epsilon problems, I will just round up. Basically, what you can do instead, if you don't use round, you can do it like this. You can use floor of this is plus 5, like this. This should also, if I have a round, I will use round. So I will just round to closest integer. This closest integer will be the integer I'm looking for. And now I have this in place. So so what I want to, I need to enter a multiplied by this divided by 100. That's all. So now let's check if I have enough integers. So I have 15 digits here. I have 1, 2, 3 digits here. So this number is about 10 power 18. So it will fit in long. So I have a long. It is long here. So sorry again. I was moved from Java, so I use long as so. So we have this 64-bit number. So it fits 18 digits just fine. So I have 15 digits here. And 3 more digits here, so I have 18 digits. 18 digits will fit in the long number. How do you round to Java? Math.round. Yes. Works perfectly fine. Okay, that was functioning. So we have 3 educational problems about how to deal with multiplication problems. Now I hope we have some problems actually. So first 3 problems was not actually problems. It's just some exercises of the multiplications. Given positive integers, consider repeatedly applying the operation. First, choose a positive integer. The defined will be represented as p power of e. P is a prime and e is positive integer. So we have some positive integer. Okay. So we have some power of some prime. Okay. Z divides n. What is n? I have this n. Z is different from all integers chosen in previous operations. So it's not a game. It's okay. So I read the name of the problem and immediately started to think how to play this game, but it's not a game actually. I just need to find the maximal number of operations I can apply to this number. So again, what's going on? I have this integer number n. And every time I apply the same operation, I choose some power of some integer of some prime number and divide my z by this this power of prime. And I want to make as many operations as possible. Yeah. So what's going on? You have this number n. Every time you divide this n by some power of prime number, what's going on is every integer number can be split into some powers of primes. So when you divide by this power of prime, the power of this prime in this n will be decreased by this e. So what I will do? I will take this number n, will split it into powers of primes. And then for each power of prime, I will calculate the maximal number of operations I can do with this prime number. And so then I will take sum of all these numbers, and it will be the total number for all operations. So how to do this? We take this number of n. Now we need to split this n into powers of primes. How to do this? I will use, actually you need to build the factorization of this number n, yes? So this n is pretty small, so it's 10 to the power 12, so I can make factorization in time of square root of n. So I will just do it like this. Like this. Let's make it long. So while x squared is no more than n, just like this. So if n divides x, x divides n, then x is some prime factor of this n. So let's calculate its power. So it's p. Okay, let's call it like here. Let's call it this p, and let's call this e. Divide and close. So that's all. Why did you write? Because I missed. No. Yes, I supposed to write this, but maybe I was talking something. I cannot talk and write at the same time. Okay. So while if this p divides n, then p is a prime factor of n. So I calculate the power of this prime factor. Now e is a prime is the power of this prime factor. Now I want to calculate the number of times I can apply this operation. So when I apply this operation, you always need to choose different power of this e. So what you can so first you apply operations like p power 1, then you apply operation p power 2, then apply operation p power 3, and so on. So its e should be at least 1 plus 2 plus 3 plus and so on plus k. So if you apply k operations, you apply these k operations, so this e should be at least this. So yeah, now you need to just find the maximal value of k such that this is not. Let's just do it like this. K equal to 0, while so this sum is actually 1 plus k multiplied by k divided by 2, right? So while k multiplied by 1 plus k divided by 2 is, so while e is at least this, I will just increase it. Yeah. So e is the power of this prime number. I just apply these operations. If I apply these operations, I need my e to be at least this. So I just calculate this maximal number of k. Yeah. So I actually find the first wrong way. So the maximum value is k minus 1. So I need to add k minus 1 to the result. So I increase k until I find the bad value for k. Yeah? So if this value is good, I just increase it until I find the first bad value of k. So the number of good values is k minus 1. And now the final thing you need to take care about is the final value of n, because if you build factorization like this, then you will find all the prime factor except the last one. So in the end, when this p exceeds square root of n, so when you then this loop is finished, you still may have one prime factor of n. That's n itself. So in the end, if n is more than 0, more than 1, then you still have some prime factor in this this n. But only one. Yeah. You may have a prime factor which exceeds the square root of n, but only one such factor. So if you finish this loop and you still have something in this n, this something is the final prime factor of n, and you still need to increase it by 1. That's all. So this 24. This 24 is basically 3 multiplied by 8. So it's 2 power 3. So from these 2, I can call operations 2 times. So I can divide it by 2 and then divide by 4. And for this 3, I can make one operation. So I have 2 operations here, 1 operation here. So the answer is 3. Here the answer is 0, here the answer is 3. For 64, yes, the power of is 2 in power of 6. So for 6 you can make 3 operations, 1, 2 and 3. The sum is 6, right? So again, the only trick you need to remember when you make factorization like this is to remember to find this last prime number. Actually, the better way to do it, to solve problems like this, is to first build the factorization and then do something. So then you will not forget to take this final prime factor. So you first make this and put all these prime factors into some array, and then use this array to calculate what you need to calculate. So you will not forget to take this final prime factor. What? I don't plan to mine any bitcoins today. Let's take the next one. N integers, and we know that I find the number of different values. What? So I don't know these integers. So I have n numbers. I don't have these numbers. So there are some n numbers, and for each number I know only the segment. Okay. And I want to find the number of median I can take. Okay, so why not? Well, it's this easy problem actually. So what values can be for the median? So what is the minimal value for the median? Minimum value of the median is when all numbers are as small as possible. So if you assign value a to each number x, so you just move each number to the leftmost possible position, then the median will move to the leftmost possible position. And if you assign this right borders to each number, so if you assign these values b to each number x, you will move each number to the rightmost possible position. So the median will move to the rightmost possible position. And that's all. And all positions between the leftmost and rightmost position are achievable, because when you can move these numbers one by one, so the median will move only one by one. So all positions between the leftmost and rightmost position of the median are may be some positions of the median. So what we need to do is to find the median of A's, median of B's, and all positions between will be achievable. That's all. Let's do it. So we need this number n. We need this to erase. Oh, it's a cat. Nice. And now we just need to find the median of the array. Let's do it simple. So I need median of the. Oh my goodness. So how to find the median of the array? The easiest way is, of course, to sort the array. So it's not integer. That's a strange way to define the median. Okay. So it's slightly more complicated. Okay. So if n is odd, everything I told you is correct. So if n is odd, that's how to solve this problem. If n is even, it's slightly more complicated. So if n is even, what I will do is I'll take this number multiplied by 2. So I will take the sum of these numbers. So I will take the sum of these two middle numbers. So I'll just multiply this median by 2. So this yeah, so like I'll just the sum of this number, and again this sum can take all possible values from the leftmost to the rightmost, because each time you can move only one number, so you can get all possible sums from the minimal to the maximal possible sum. So that's slight deviation. So again, okay, let's say n is the size of this array. So if so if n is odd, you just return the middle point. So middle point will be n over 2. So if n is even, I will return this, that is sum of these numbers, plus minus 1, right? Minus 1 is the left one. Yeah. Yeah. If we calculate from 0, then minus 1 is the left one, and it is right one. Yeah. I think that's all. Yeah, I think that's the whole solution. Okay, let's live with this problem. So you have three possible values. The minimal value is 3 over 2, so it's 1.5. Now you have 2, and then you have 5 over 2. So this is the minimal value, this is the maximal value. And all middle value, all values between are also achievable. Okay, and the final one. Given a sequence of n positive integers and another positive integer s, find the non-empty subset of the set. Let's define number of different non-empty subsets of T such that find the sum of f of t over all subsets of S. So this is small, so it's just an abstract, right? Again, so what we need to calculate for each so we have n integers. For each for all this, we take all possible. Well, it's minus 1. Non-empty subsets, okay. Non-empty subset, okay. Okay, for empty subset, it's obviously 0, so it doesn't matter. So we take some subset of these numbers. For this subset, we calculate the total number of all its subsets with sum equal to s. And that's all. Now we just calculate sum of all these numbers. So we take the whole set of numbers, take some subset of this number, and then take the subset of this number with sum equal to s. And that's what we need to calculate. How to learn sports programming? Just solve contests. It's nothing interesting, just suppose. I bring some new pens. So what we're doing here, we take all these numbers, yeah. So these are all possible numbers. Now we take some subset of these numbers. Let's take, and from this subset we take some another subset. And in this subset, the sum should be equal to s. And we need to calculate this total, the sum of all these values. So sum of all these values will be just the number of tuples like this. So we take some subset this, and then from this set we have some subset with sum equal to s. And the sum of all these functions f, for all these subset, will be the number of these pairs. So we need to calculate the total number of pairs, like subset, and then subset of sum equal to s. Let's call this A, let's call B. Yeah. So we need to calculate the total number of different pairs such that B is subset of A and sum in B equal to s. So the number of these pairs will be equal to sum of all these functions f. Because again, for this A, if you take for A, will be number of B's, yeah, of B, yeah. So for each A, function f is just number of different subsets B. So if you calculate sum of all f's, it will be, for each A we calculate number of B, so it will be just total number of pairs. Yeah. So that's what we want to calculate. How to calculate possible number of pairs? So what's this number? We take some subset and then take subset of some s. So if we know this subset B, we can find the number of its supersets. How to calculate number of supersets? It's simple. So you have some subset. So imagine you know this subset B. So for this subset B, you just need to find the number of its supersets, right? So how to find numbers of subsets? You just need to know the number of elements in this subset B. So if you know the number of elements in B, I cannot know the number of B. No, it's easy. It's easy. Plan B. So let's paint all these numbers in 3 colors. I have a lot of markers. So let's color all the elements in 3 different colors. Why? Oh, so check this. Let me just fix the camera. Camera is not working. Which one? This? No, this one. Oh, it's fine. Oh, much better. So let's color all these elements in 3 different colors. So first, let's take the elements which are inside the set B and color them red. Now let's take all elements in set A, but not in set B, and color them purple, because I have purple marker. So let's color all these elements purple. And color all other elements with something like this green. So, oh, that's all. That's all. And now, what you want to do? is to find the number of different colorings. So you need to color all elements in 3 different colors, like at least red, purple, and green, such that sum of these red numbers, will be equal to S. That's all. And you can calculate this number using dynamic programming. So I will go from left to right, and for each coloring I need only to know the sum of these red numbers. So I'll take dynamic programming, which calculates the number of ways to color all these numbers in this prefix, such that the sum of these red numbers equal to S. What search algorithm? What do you mean? I will use dynamic programming. So if it is search algorithm, let's move it a little bit here. So you can see both the paper and the code. Let's go. So let's read numbers. N and S. And now we'll just use dynamic programming. So how to use dynamic programming? Now again, you need to solve an abstract problem. What is the easiest way? Okay, let's solve it the hard way first. So this array D will contain the number of ways to color this prefix, such that the sum of these red numbers equal to I. So this sum is in range from 0 to S, so it's S plus 1. In the beginning, I have empty prefix, so I can color empty prefix one way, such that the sum equal to 0, so 0 is 1. So this is the only way to color the empty prefix. Just color nothing and the sum is 0. And now I'll iterate properly. So now I take this number x and I want to update my dynamic programming. So again, I will do it in the hard way. I will do it like this, just for simplicity. Now, let's render all possible values of the current sum. So I is my current sum, so I painted this prefix and the sum of these red values equal to I. Now I have 3 possible ways to color this new number. I can color it in green, in purple, or in red. If I color it in red or in purple, then my sum doesn't increase. So then sum is the same, and the number of ways is like ti multiplied by 2, because I have 2 possible ways to color this new element. I can color it in purple or in green. Now I can color it red. If I color it red, then my sum will increase by x. So if this I plus x is s, I can color this element red. So my new sum will be I plus x. So I plus x, like this. Now don't forget to calculate it model. So you can always calculate it model this value. So now instead of doing this, I will do it like this. Oh. Okay, let's do it like this. Okay, let's do it. Just everything long, just for simplicity. That's not the fastest way to solve it problem, but it's the most simple way to do it. That's all. That's basically the whole code. Now in the end, you want to calculate the total number of ways such that the sum of red number is exactly s. So just output the value of s. Can't we do contribution to sum here? What? What? So you want, so if the sum is exactly s, you want to add this result and this value to the result, you can do it. Yeah, you can calculate the resulting value in the middle. So if you have some prefix and the sum equal to s, you can add it to the result. That's another way to solve this problem. But that's easier way just to calculate dynamic programming. In the end, have this value here. Problem request for channel points functionality. I have no idea how to do it. I may learn how to use Twitch actually. I'm not that advanced Twitch user. You can request problem in the chat. I will try to remember it. Yeah, that's actually a nice code. I think it should work like this. Yeah. That's not the best way to solve the knapsack actually. You can solve knapsack problem with one-dimensional array. So here I just reuse this arrays every time. It's not the best way to solve knapsack problem. No, but still it's fine. So you can optimize this dynamic programming by using only one array, because each time you move to the right, so when you modify values, you only modify values to the right from the given values. So when you start from I, you only modify values I and I plus x. So you can go from right to left and use the same array. Okay, so I get it. But it works even without these optimizations. Huh? That's all. Okay, so what's the results? So we have only one failed problem. Yes. So we failed actually a very easy problem, just because we're too stupid. Okay, that was close. So we may finish this contest without bugs, but okay, it happens. So what is the problem from let's see. Let's define the cost of string s, number of index pairs. I mean, there is a tutorial, so why do you want me to solve this? Let's define the cost of the string number of index pairs such that so we have the same. So I want to find number of pairs of indices such that I have the same character here and I have the same character here. Okay. You are given two positive integers n and k. Okay. Among all strings with length n, it contains only the first k characters. Find a string with minimal possible cost. Minimum possible cost. Ooh. That's interesting. So the cost is just number of equal pairs. So we have pairs, two pairs of characters. So I have I equal to j and I plus 1 equal to j plus 1. Just concatenates all permutations. And what will happen if you concatenate all the permutations? Now basically, you want to concatenate all possible pairs. Let me assume. So when the answer is 0, then all pairs are different. All pairs are different. So how many pairs do I have? I have like k square possible pairs, right? So I have k square possible pairs. Is it possible to have all k square possible pairs in the same string? Yeah, I think it should be possible. Yes, because this graph is actually, let me show. Up. So what's going on here? You have k characters, so you have k square possible pairs of characters. So you want to construct a string such that all pairs are different. So how to construct a string? Imagine you have three characters. You have like A, B, and C. So there are 9 possible pairs. Yeah. So there are like AA, AB, AC, BA, BB, and so on. Yeah. So there are 9 possible pairs. So we want to construct a string such that all pairs are different. You have all 9 possible pairs. So how to construct such a string? You construct this. You can construct a graph like this. So every edge of this graph is a pair of integer. It's a pair of characters, and you have this graph like this. This is obviously an Euler graph. So you can build the Euler tour in this graph. And if you build Euler tour in this graph, you will get a string containing all the characters. So, let's build some Euler tour on this graph. So you can do, for example, you can go here, then here, then here, then here, then here, then here, then here, here, and here. Yeah. So if you do it in this way, you will have string like A, B, then you have this loop. So we have B, then go back A, then take this loop, then go here, then make this loop, then go here and back. So B and then C, and then go back to A. So now you have this string. This string contains all possible pairs. So, no, again, now for this string, the answer is 0. Yeah. So the cost of this string is 0. Again, the cost. Again, this is the cost of the string. The cost is number of equal pairs. In this string, you have 0 equal pairs. The cost is 0. So if this n is at most this k square plus 1 plus 1. Yeah. If n is at most k square plus 1. Yeah. Then you can build string like this, and all pairs will be different. If n is more than k square plus 1, then you will have some equal pairs, because just you have not enough different pairs. And again, this cost will be minimal when you have like the same number of equal pairs for each pair. So you basically you want to split all these equal strings in different pairs evenly. So if you want to construct a longer string, you just repeat the same pattern several times. So for each string will come up exactly once in each of these. So if you want to build longer string, you just repeat the same pattern again. So again, you have B, B, A, A, C, C, B, C, A. And now each string will come up exactly twice. So we have this string bb here and this string bb here. And if you do it like this, the cost will be minimal because you like split all these equal strings evenly among all possible pairs. That's the whole plan. That's the whole plan. Now I just need to construct this string. What's the easiest way to construct this string? I don't want to... No, you can just run a build earlier on this graph. Is it the easiest way? What's the easiest way to construct this string? I don't know. What is the easiest way to construct a string besides this building the Euler on this graph? No, I can build Euler. It's not a big problem, but maybe it's just easier way to do this. So we have this full graph, and you just need to build Euler in the full graph. What is the easiest way to do it? I've never thought about this. De Bruijn? What? What? What do you mean? I know, I'll just build the Euler because I can. Let's just build the Euler. Yes, we have the full graph, but how to build Euler in the full graph? Brilliant secrets of order 2, the alphabetical is like this. This is the educational part of this stream. I have no idea what it is. So how to build start using internet path. Yes, that's what I plan to do. And walls can connect together in this graph all Linden words find the right end. It doesn't look easier. And where's build with some computer great quite paint for the folder. It's in shift is with paint fields. It doesn't look easy. Okay, this is to start at I and then on each step at the maximal valid letter. Maximal valid letter. Oh. And why does it work? That's interesting. Let's build back. Let's move to the string later. While I always also used this, no, so while I used pair from S back J++, so I find maximal validator. Maximal validator. Is it important? And start with AA. Okay. I'll just believe in you. Okay. So so this should build the De Bruijn sequence for 2. Let's hope it works. So now I build this sequence, and that's all. And that's all. Can you stop this? So I start with AA, right? So I will finish with A. Yes. I'll just remove this 0. Yeah. Now I just need to construct the result. I will construct the result. I'll just take the number modulo just like this. There's too many iterations. What? What do you mean too many iterations? That's okay. I'll just believe. I believe I can fly. What? It's not working. It's not working. Yes. I used one here. Yeah. It's my bad, my bad, my bad. Okay. That's a cool. Yeah, that's nice algorithm. I need to learn why it's working actually. It's nice theory. So what's next? Let's solve one more. We have enough time. Yeah, we have plenty of time. Let's solve one more ABC. Tutorial doesn't have how to construct. Let's read the tutorial. I can build it. That's a very valid solution. You can build this graph of 26 vertices and just build the Euler cycle in this graph. That's actually this working algorithm. You just do it like this. Just build this graph and build the Euler cycle in this graph. Totally works. We can prove that this graph is a Euler graph, so you will find the Euler tool in this graph. That's just more tricky solution. You need to prove that this actually works. But this solution is obviously correct. Do minimum maybe. So there are some greedy ways to build this Euler tour when you know that your graph is a full graph. So when you have a full graph, you can build Euler tour with this greedy solution. That's interesting. But you can do it using standard algorithm for Euler tour. It definitely should work. For 26 vertices, you can do it just almost any possible way is correct. Okay, let's have one more. Okay. That's fun. I do it like this. Just for fun. Five. Okay. That was flex. Okay. It was a friend each some link range or a total for legs. Okay, X animals and I have Y legs. Determine whether the combinations combinations which is correct. Okay, so we have X and Y. First we need to check that number Y is even. has hardly 2 or 4 legs. Now, we need to check that number of legs is at most x over 2. Yeah? And we need to check that it is no more than x multiplied by 4. So if it is even, it is at least this and at most this, then we can have this combination. Because we can start from this combination of only herons and then swap every crane with turtle. Each time we increase total number of legs by 2. Yes or no? Okay, let's move next. Integer sequence of length n, so given an integer x and integer sequence among the integers not contained in the sequence, find the integer nearest to x. What does it mean? Find the integer whose absolute difference with x is the minimum. If there are multiple, what's the smallest? Okay, among the integers not contained in the sequence. This integer is small. I have very small integers. Okay, there are multiple ways to solve this problem. Let's do it like this. Okay, these numbers are small, so I'll just make array of booleans. So I'll make array of booleans. So for each number, I will remember if I have this boolean in my set or not. So I have booleans of size, so from 1 to 100. So I need array from 0 to 101. So it's 102. Like this. Now for each values in P, I will just mark this number as true. So now for each number, I remember if I have this number in my set or not. And now I will iterate all possible differences. So difference is from 0. So when x is bit. So now I have this difference d, and I want to check if I can have a number with difference d not in my set. So I check if this number x minus d is not in my set, so if it's greater than 0, and if it is not in my set, then this number I'm looking for. So I will just output x minus d and break. And if number x plus d is not in my set, if for example this is yeah, I believe that's all. If these numbers are big, it's actually quite more complicated. But it's actually the same problem, but instead of having this array, you can have a set. So actually, if these numbers are big, you can do the same trick, but with sets. Let's submit this first. Actually, you can remove this. It's working, right? It's working. I actually need, you don't need these checks. because you will never get out of this, because you will break when you see the first yeah, so actually you don't need this. Yeah. If these numbers are big, you can do the same trick, but you have array, you have set instead of this array. So you just make this, and here you don't. In simplification, you check if find x minus j equals to n, like this. The solution works in linear time because for each number will be checked only once, and you break from this loop as soon as you find the number which is not in your set. So you can make at most n iterations of this loop. Let's just yeah. No, it's actually even faster. But it's I don't think it's first. I think it's just error in the execution time. So it's not fast. It's actually slower than using arrays. But for these small constraints, it doesn't matter actually. Okay, problem D. Given is a number a sequence S of length n from number x to for property. What? Find the number of integers for every integer j not equal, does not divide the I. Okay, so we need to find the number of elements of this sequence such that there is no divisor of this element in the sequence. Right? Okay. 2, 3, and 4. 2, 3. So these three. And you have another. So each of these has a divisor. Yes. Yes, it is. Yep. Okay. So what is the easiest way to solve this problem? So I believe the easiest way to solve this problem is actually just to have an array of all possible values. So I have million possible values of these numbers. So I will, for all possible values, I will check if I have a divisor of this number in my sequence or not. Yeah, so if I do, I just iterate all multiples of this number and mark them as bad numbers. Yeah. Здравствуйте, товарищи, рад вас всех видеть, заходите. Мы тут решаем задачки. Развлекаемся. Я не попадаю по кнопкам еще. Так, значит, нам нужно завести массив размером на 10 в 6. Такой нужно завести размер на все плохие числа, чтобы так. Шо? Плохой юмор. Юмор плохой. Yeah, first let's solve this. Let's sort this array. Yeah. Now we just iterate all elements of this array. Yeah. So if this element is actually good, so if not marked, then this element is good. So I will increase the result by 1. And now I need to iterate all multiples of this x. So for y equal to x, so y less than max, y plus. So I iterate all multiples of this x and mark them as bad. That's all. Yeah. Yeah. Ah. Too bad. Seconds I'm not working. Стрим пролагивает иногда, к сожалению, сорян. Еще с интернетом сегодня что-то не то. Иногда нормальный, а иногда что-то пролагивает, не знаю. Что-то с интернетом в наших краях сегодня. Бесит. So if I have two equal numbers, then I need to yeah. So if I is less than -1 and I equal to I plus 1. So if I have two equal numbers, then I don't need to increase rs. Yeah. That's sad. That's actually sad. It was not necessary, but okay. No, do infant series at quarter number of month and can get another from 1 to 3. Okay, infants and kindergartens. Okay, infant has rating AI and initially belongs. Okay. From now on, co-transfers will happen. After transfer, infant C will belong to kindergarten D. Okay, so we moved infant from one kindergarten to another kindergarten. Rating doesn't change, okay. Here we define the evenness for each kindergarten with one or more infants. Find the highest rating of all if infants in the kindergarten. The evenness lowest among these ratings. Find evenness just after the transfer. So we just move infants from one to another. For each non-empty set, we find the maximum and then calculate minimum. So what's the easiest way to solve this? What's the easiest way to solve this? I can just use the sets. In C++ you can make an array of sets. So for each kindergarten you can have a set of all children in this kindergarten. Yeah, that's actually maybe the easiest way to solve this problem. Yep, let's do it like this. I do it like this. So they all start from 0. Let's just do it like this. So let's have vector of set. Actually, multiset. How multisets work? I never used multisets in C++ because I'm too scared of a multiset. Let's try. So for each kindergarten, we'll maintain the multiset of all ratings in this kindergarten. We have C. We need one more letter. P. Max. Okay. We have yeah. So we have this number of kindergarten. For each kindergarten, we'll maintain the multiset. So if this set is not empty, I will add its maximum. Maximum is can I do it like this? Let's work like this. So this will be the maximal element of this subset, and I will end this element to this all. Now my result is the minimal element in this all. Yeah. Now each time I make this operation, so I do this C and D yes, and see. Now I need to move this infant to this. So first I need to remove this kindergarten from one kindergarten and then move it to another kindergarten. So how to remove this child from this kindergarten? I take this kindergarten. So I have this kindergarten X. So this is the current kindergarten of this infant. I need to remove it from this kindergarten. First I will need to remove this erase current maximum. So I remove it current maximum from all, and I remove its rating from it. So now I removed this one child from this kindergarten. No, I just erased it. Now I need to, now I need to put it back. So if it's not empty, I need to put back the new maximum. That's good. So this calls remove one infant from one kindergarten. So I remove current maximum from all, remove this element from this kindergarten. Then if it is still not empty, I take the new maximum and put it back to all. And now I do the same when I insert this element in kindergarten. So x equal to d. So I put this element in the kindergarten. So first I erase current maximum from this kindergarten. I insert is equal to d, like this. So I remove again this current maximum from the set of all maximums. Then I insert new element into this set. If it is not empty, if it is not empty, if not empty, then now it's definitely not empty. And now insert it and then put this maximum back. In the end, I just need to find minimum in this set P. No? Ni P. Oh. Yeah. Is the race works like I expect for this multi-set? Elements. Can I move only one element? Uh-huh. Uh-huh. Now let's try to fix every place I use this erase. That's why I never use multisets, because I'm too scared of it. Function. What? What? What do you mean? I think it should work fine. That should work. It's not the best way to solve this problem. It should work. No? No, it's working. Yeah. Yeah, I changed it to 10%, yes. Okay, I hate these multisets for some reason. Maybe because I'm not using them very often. So this final one. Okay, this is the last problem for the day. Stock comfort straight over if single component with single grid left space square so have what sleeve and can be entered. Okay, the square space is right. Okay, so we have this map. Okay, in one stroke can move between 1 and k squares or one of the 4 directions. So we move not 1 square but several square from 1 to k. The move may not pass through the square of lotus leaf. Okay, makes sense. Moving such square of the point was also forbidden. Find the minimum number of strokes Snook takes to travel from square. Oh, it's big. Oh, that's fun. That's a fun problem. I have almost the same problem in my lectures about shortest paths. So again, what's the problem? You have this map. And you have 2 points on this map. You want to travel from one point to another point on this map. And each time you can move not 1 square, but up to k squares in one move. That's all. And what you want to do is to find the minimum number of moves to get from one point to another point. What's the easiest way to solve this problem? Let's think. What's the easiest way to solve this problem? There are several ways to solve this problem. One of the ways to solve this problem is to use something like breadth-first search. So you can use breadth-first search for this problem, like the regular breadth-first search. You have this graph. From each point, you make these edges to the nearest k points. But if you just do it, okay, let me draw. So what you can do is to make a standard breadth-first search. From each cell you can move not to, usually in breadth-first search you can move to the 4 neighboring cells. But in this problem you can move to all these cells. So if you just use standard breadth-first search, you need to make edges to all these nodes. So what you can do is to change your breadth-first search algorithm in the following way. So you can start from each point. What you're doing in breadth-first search, you take the vertex from from the queue and find all the vertices reachable from this vertex which are not marked yet. So you need to take all these nodes and find all not marked vertices in this range. You can do it, for example, using almost anything. Let's see, you can use it, you can do it using disjoint set union, for example. Perfectly fine. So you need the fast way to find all non-marked vertices in this range. No, easiest way to do it is to, for each point, find the closest non-marked point to the right. So for each point, you will find the closest point to the right, which is not. So you have this range. Yes, some vertices are marked, some vertices are not marked. Yeah, so you're now standing here, you want to find all vertices in this range not marked. So you want to find these vertices and mark them. Because if you're standing here, you can move to here, here, and here in one step. Easiest way to do is to start from here and make a procedure which finds the next unmarked point to the right. So you start from here and find this point, mark it, now find this point, mark it, now find this point, mark it, and so on. And you can do it using union find data structure. I think this is the easiest way to solve this problem. There are other ways to solve this problem. You can use sets in this, but I think, yes, for a million, I think you can use sets also. Yeah. So you need to find the all elements in the range. You can do it using sets. For this set, you can call a lower bound for this left border, find the next value, and so on. Yes, I think you can call lower bound a million times. It's not a problem. Maybe that's the way to go, actually. Yeah, maybe this is easy, actually, to use disjoint sets, but disjoint sets will be much faster than sets. I'm not Marian, sorry. It's not my name, not my surname. Yeah, I think that's what we do. We will use sets for each. So for each row, we will have a sets of all non-marked vertices in this row. So when we need to find the element, we will start from here, find the close value here, and so on. Yeah, I think that should work. That should work. So let's go. So we have HWK. So we have x1, y1, x2, y2. So x is the row, y is the column. Okay. Now they're all from 0. Now we need to read the map. Yep, that's all. Now we'll make this recess vector of set. I'm always a little bit scared when I have a million elements in the set. We have a million sets, but in C++ it should be fine. That's why I love C++. So I need these rows. So for each row, I will have this set of integers in this row. And for each column, I will have this set of integers in this column. Yeah. if this cell is empty, if ij equal to, then I will put this as a vertex in both these sets. So I will put it in the set CRI insert JN CJ insert yeah. So now for each row I maintain the set of all empty cells in this set, and for each column I maintain the set. And now I simply make the breadth search. Let's make breadth search just now let's make a queue of pairs. So that's my queue. First I insert push pair x1 y1. So that's my starting point. And I also need array of distances. It's no normal breadth search, just in this strange graph. So this is array of distances for my breadth search. This is my queue. Now I push this element, distance will be 0. If I this print -1. Okay, let's fill the rate with -1s. Now distance to this first position is 0. And now I need to remove this position from both these sets. So I will remove y1 from this set, and I will remove x1 from this set. That's all. Now we make a standard breadth search. So while Q is not empty, we take one, let's take pair front, yeah. So we take the pair from the queue. This is our current vertex. Now we need to move from this vertex to all neighboring nodes. So let's do it. So we need to find all. Not exactly. Not exactly. We cannot jump, so we need to find, yeah. So we need to find the closest obstacle in both directions and find the only in the segment between these two obstacles. Now I don't like this. Now I don't like this. So we need another. Set of obstacles. Okay, let's just. Okay, so this will be set of obstacles. Don't like this. Now I don't like this. Okay, let's finish it like this. That's good enough. It's just not, I believe it's not the best way to solve this. But it should be good enough. So now we're standing here. We need to find, okay, let's do it. So we need to find all the values in this, let's just move here. Let's make a function. Okay, we'll make a function. We'll return. Oh, let's return the vector. Find all. So we're given the the set of obstacles, the set of nodes, and the current position. And we need to find in this k. So this k is the radius, yeah? So we need to start from this point and find among all valid positions, find all positions inside this set. So we'll return all positions in this set which are accessible from this point x. So they are not farther than this k units from this position k, and they also do these obstacles do not interfere with this. You got it, okay. Yeah. So the leftmost position is x minus k. The rightmost position is x plus k. But there may be some obstacles. So how to find the closest obstacle? So closest obstacle to the left. So we need to find element less than x. So we need to find pointer in obstacles, find lower bound of x. Yeah. So if p is not or begin, then I make minus minus p, and that's the closest obstacle to the left. Yeah. And now we update the left value. So left will be maximum from L and P. Right? And if this P is not the last one, then this is the closest obstacle to the right. So we update the right border. Minimum from R and P. So now this is from L to R is the range we're looking for. So now we need to find all values in this set V inside this range. Let's also remove them from this range. Yeah. Can I do it once? So I put it into set V and then remove it. Yeah. Yeah. So here I find the if it is not and it's less or equal than R. So I find the closest element to my left border if there is an element and it is less or equal than R, then I put this element in my result and remove it from this set. Yep. Yeah. Now, first let's check. So in my row, I need to find. Now, in my row, I need to find all elements in this segment. So I start from my row, find all. Set of obstacles are all of. So I take my row, I take element my row, and this is my position, and distance is k. So these are all possible, all positions in my rows. Now I iterate all positions in my row. So yes, it may be visited also. It may be already visited. So I need to check if it is not visited yet. If dxy2 is -1, then it's not visited yet. So now I visit this. And put it in the queue. Yeah. And now I do the same with my columns. So I find all possible x's. So I need to find columns of y and column of y from point x. Distance is k. Now I take all x's in this set. 1 x2 y x plus y x2 y. What? Why is it gray? Where is the gray? I use this P here. Okay, let's change. I believe that's all. And now I just need to find the result for the so I find the result for x2, y2. After updating state, we can add one. Okay, then we want to rotate this. What? So we add 1 over k. I think it's a little bit overcomplicated. Should be solved easier. Cool. 1.1 seconds. And what is the time limit? Time limit is 3 seconds. Is there an easier way to solve this? Oh. Dijkstra algorithm. Yeah, that's also possible. Yeah, that's another. Yes, that's another way to solve this. You can use Dijkstra algorithm. You can maintain the weighted graph, so the distance to your node is the number of steps plus the number of how it's called? I don't know how it's called. So it's number of steps plus distance. Actually, you just split your step into small steps. So you can split each big step with up to k small steps. And now the distance is pair of number of big steps plus number of small steps. You want to optimize the number of big steps, and from this you optimize the number of small steps. You optimize this pair. That's also working. Yeah, and now you simply make a Dijkstra in this graph. Yeah. Yeah, like this. Yeah. I don't think it's actually easier to implement, because since you need to implement this Dijkstra algorithms, also you need to maintain the direction. So in this solution you need to maintain your current square and your direction, because you cannot change the direction between steps. So your current state is square plus direction, and in this graph you build a Dijkstra algorithm. So I think it's more complicated than our solution, but still fine. Time complexity is the same actually. In this solution we also have this log factor because we're using these sets. So here we're using these set operations. So each set operation costs you log n time. So actually for each cell we spend log n time to make these operations. And here it will be the same. Yeah. Cool. So I don't want to start on the code. So there is another problem. So someone mentioned another problem in the chat. Let's check. Up. So it's E from div2. Okay, div2 E should be approachable. Usually, not always. Have done destructive mathematics, ancient mathematics, special person. Okay, 1-digit positive integer. Okay, so you have simple expressions when you always have brackets and all integers are 1 digit. Okay. Distribute for one piece of first being variation as a result, operations were erased, keeping only the numbers and the brackets. Since we formalized its hand challenged the following task. Given the number of plus and minus operators, the original expression, find out the maximal possible value for the expression on the papyrus paper after putting the plus and minus operators. Also, it is square. What is P? Plus and minus operators, okay. So one of these numbers is at most 100. Okay. It looks like a normal dynamic programming. So you build a tree from this expression, and in this tree, for each subtree, you need to calculate minimal and maximal value in this subtree. It should be fine. Let's solve this really fast. Every time I say I will do it really fast, it ends up with 1 hour of debugging. Okay, let's try. So what we're doing? First we will read this number, P and M. Now, what we need to do is to parse this expression. So we parse this expression and build a tree. Yeah. What's the plan? You have this expression. Let's say this. So what I want to do is to build a tree, which is so I have 2, and here I have 1 and 2. So I want to build this tree from this expression. And now, using this tree, I will calculate the dynamic programming. Yeah, I think it's the easiest way to do it. Is it? Yeah, I think this is the easiest way to do it. So I will just parse this expression and build this tree. Let's just write simple parser of the expression. So this parse will return the node which is root of the parsed tree. So if this is a digit, then we just parse this digit and return it. So we create okay, let's. I think not today. I think it's too late. So it's the final problem for today, I think. Maybe just a quick look. So if we read some digit, we just create node of this digit. So we create a value of SS car minus 0. So this is the value, and -1 -1. And move cursor. Okay. Now, if I have a bracket, now I have a bracket, so I will move the bracket. Now I read the left part. Now I have this question mark. Move cursor again. Parse the right part. And now I have the final bracket. And now I created this node. Let's put 0. L and R. That's all. Now we parsed all this. Yeah. So we parsed this expression into a tree. And now we just call it dynamic programming this tree. How to make it dynamic programming? So for each node of this tree, we will find the minimal and maximal value we can get inside this tree when we have this number of pluses and minuses in this subtree. So for each subtree, we know the number of pluses and minuses. I hate this example. So, what is the easiest way to do it? What is the easiest way to do it? Okay, let's do it in an easy way. So we'll create dynamic programming again. So make dynamic programming. Let's do it recursively. Yes, let's just do it recursively. So vector int. Just like this. So we'll create array of size of the. So for each node, so it's we need to create vector of the size of the maximum possible. I actually hate this. So I need to know number of minuses or number of pluses. Okay, let's make two possible cases. Okay, let's do two possible. Okay. That's question E from contest 465. You can Google it actually. There is a search in the problem set. Okay, so for each tree size. So we need to find all values from 0 to mx, so it's max plus 1. We need the pairs, we need, okay, let's put two arrays. So in a field, I can find the minimum and maximum value. I'll fill it with something, so we'll fill minimums with int max, and I've found maximums with int min. Yeah. We just start from root and calculate it recursively. You have node x. You want to calculate value in the node x. You check if it's actually leaf. It's leaf. Then dp max equal to dp mean max of x and 0 equal to mean x and 0 equal to the value of this leaf. So for the leaf value you have 0 operators and 0. Yeah, you have 0 operators and the value is this. Now if not, then you need to put something in the left subtree, put something in the right subtree. So you first you calculate everything inside the left subtree. You calculate everything inside the right subtree. And now you calculate value in your node. So in your node, you put something in your node, plus or minus, and then put something in the left subtree, put something in the right subtree. Yeah. So you iterate all possible values in the left subtree. Put something in the right subtree. Okay. Okay, you put this in the left subtree, this in the right subtree. Now you put something in your node. You can put plus or minus. Okay, let's say 0 is plus, 1 is minus. So if you use plus, then the total number of pluses will be I plus j plus okay. So let's see, if we use pluses and t equal to 0, then k plus plus, or if we don't use plus, if you use minuses and t equal to 1, now k is the total number of these signs we are counting in. So one of the signs, one of the operators minuses or plus is small. So we use one of these operators here. So we use this number of operators in the left subtree, this number of operators in the right subtree. Yep. So this is the total number of operations. Okay, if k is more than x. Now, okay. Now, if t equals 0, then the minimal possible sum xk will be minimal. No, gp maximum possible sum will be maximum of current plus maximum possible sum, and maximum left plus maximum right. Plus like this, and I don't want to have these infinities. So I update my maximum value, I update my minimal value. Minimum is just minimum of my current minimum and sum of two minimums. And if I use minus, then maximum will be when I use maximal value in the right and minimal value in the left. And minimum will be when I use minimum value here and maximal value here. So here I use plus, here I use minus. I believe that's all. Yeah. Okay, let's run. Just try it on a samples. Just to check it. Oh, it's not working. 5. Why 5? Yes, I should have 1 minus and 1 plus. And when I use minus, minus, okay, here. Makes sense, okay. Minus 1. No, it's 2 plus 1 minus 2, right? So here we have minus 1, and here we have 2 plus minus 1. Yes. So what's the problem? Again, we put minus here, so it's 1 minus 2. Use plus is false, so we go here, and when t equal to 1, we increase the key. So here it is 0, 0, here it is 1. And now here it is 0 and 1. It is 0 here, 1 here. Yes. That's right. Okay. "31 milliseconds. It's that fast. Actually, it's quite surprising. Actually, it's only 100, so it's 2. Yes, okay, it's not surprising. Let's check. One more. Oh no, it's the same. Today problem. Problem E today. Given n segments from round n is segment color from the value. Let's just to select subset of these segments. Subset of the segments. Okay. Once subset selected, it's possible to travel between two integer points if there exists a selected segment which covers both of them. A subset is good if it's possible to reach point M starting from point 1. The cost of subset is the difference between maximum and minimum values. Each segment has a value between maximum and minimum values of the segment. Find the minimum cost of good subset. That's interesting. So basically, you need to cover all the points from 0 to m using these segments, right? So if you sort all the segments by the value, you actually need to take a segment from this array, yes? Because if you you can take all segments with values in this range. So if you select some range of values, you can take all segments in this range. So you can use two pointers method in this array of segments, but you need a good way to check if the current solution is good or not, right? Well, I can do it using segment tree. Is it good enough? Just 6 megabytes. It still should fit. So what you can again, how can you solve problems like this? So you have all your segments, yeah. So you sort all your segments by the values. Yeah. So you have all your segments, right? So you sort this array of segments by values. Now if you take the in your set you have the segment with minimal value and segment with maximal value. You can take all the segments in between. But if you add segments to your set, it still is good. Yeah. Now so basically you select some segment in this array of segments and take all segments in this segment. Okay. And now you need to find a way to check if you take these segments, you will have a good set of segments. Yeah. So how to check if the set of segments is good? So you need to travel from 0 to m using these segments. So we have some segment here, here, and say here, and something here and here. So your set of segments must cover all the whole range from 0 to m. So you start from here and you travel from here. So you basically need to check that your set of segments covers all range from 0 to m. And now, what you need to do is to find the smallest segment such that if you take all segments in this interval, yeah, then this set of segments is good. It is good means that it covers whole range from 0 to m. What you can do is you can do two pointers method. So you take this L, this R. You take all segments in this range from L to R and check if this set of segments is good. And now you just use two pointers method. So you move one pointer, then move another pointer, and so on. I have the whole lesson in Codeforces about two pointers method. It's quite powerful method. The only thing you need to implement when you implement two pointers method is to update your result when you move one of the pointers. So when you move one of the pointers, you need to update your result. So you need to check if you updated. So you add one more. So what happens? You move the right pointer here. Now you have one more segment in your set. So you add one more segment to your set. So when you move this right pointer here, this segment is now in your set. So you add the segment to your set. You need to update your result. You need to check if your current set is good. You can do it using segment trees. So using segment trees, you can add segment, remove segment, and check if your set of segments covers the whole range. Basically, when you add segment, you make +1 on the segment. When you remove segment, you make -1. And then you can check, you need to check that the whole range doesn't contain zeros. So you take minimum on the whole segment, on the whole range, and check if this minimum is not 0. So you need a segment tree which can add, we can increase the segment by 1, decrease segment by 1, and find the minimum on the segment. You can do it using segment trees. Again, you can watch my lesson about segment trees. So these are good operations for the segment tree. You can increment, decrement, or find the minimum. So you can make segment trees for these operations, and now use two pointers method to find the best possible segment which is good. I don't want to implement it right now, it's too late. It's almost 3 hours of streaming, but it's actually not that. Did they post the editorial? What about the editorial? Yeah. So they didn't post it earlier yet, but I think that's what they expected. So again, what you do? You make you sort all the segments by value. Now you need to find you find interval in this array and take all segments in this interval. You can do it using two pointers method. When you implement two pointers method, you need to be able to insert elements in your set and remove elements from your set and update the result. And you can do it using segment tree. So you use segment tree to update your result, and then use toPointers method. That's all. Взломы идут. В смысле, а разбор... Так, может, я зря разобрал? Может, я зря разобрал? Может, еще рано разбирать? Ну, там же объясняют сейчас. Ну, там же обсуждали уже решение. Не, можно обсуждать. Окей, можно обсуждать. Просто еще не выложили разбор. Ладненько, я надеюсь, понятно все стало. Еще раз рекламирую, у меня вот эти прекрасные, вот здесь прекрасные занятия про два указателя. То есть прекрасное указатель про два указателя. Вот, так это не мое. Вот, есть два указателя. И есть прекрасные занятия про деревья отрезков. Посмотрите, вот это занятие и то занятие. И все будет понятно. Но не сразу. Так, ладно, все на сегодня. Что-то я 3 часа уже сижу, я уже немножко заговариваюсь. Может, завтра еще соберемся. Если завтра будет не лень, я завтра еще одно проведу. Завтра, правда... Завтра контест, да? А завтра раунд 4, да? Сейчас. Да, у нас завтра раунд 4 топ-кодера, поэтому не уверен, что завтра будет. Но посмотрим. Ладненько, всем покасики. Заходите еще. Спасибо, что посидели. С вами, конечно, веселее, чем одному решать. Одному решать очень скучно. А с вами ничего. Кидульки.